Welcome to another journey through the cosmos, where we'll unravel one of astronomy's most fascinating mysteries. I'm here to guide you through the story of how humanity completely misunderstood the very nature of galaxies for centuries, and how our cosmic perspective was turned upside down in ways that would make your head spin. Before we dive into this galactic tale, I'd love to know where you're listening from tonight. Are you perhaps gazing up at the Milky Way from your backyard? Or maybe you're curled up indoors while the universe continues its eternal dance outside your window. There's something beautifully fitting about discussing our cosmic misconceptions while we're all part of the very galaxy we once failed to understand. If you find yourself drawn to these stories of scientific discovery and cosmic revelation, I'd be grateful if you'd subscribe to join our community of curious minds exploring the universe together. Also, it would help me cater my first 1,000 subscribers and help the growth on this amazing channel. The visuals are here for you, but there is absolutely no problem if you doze off midway through the video. Feel free to close your eyes, breathe deep, and let me take care of the rest. Now, imagine this scene from the early 1900s. The world's most brilliant astronomers gather at observatories, peering through the most powerful telescopes of their time. They're looking at these strange, fuzzy spiral shapes scattered across the night sky, and they're absolutely convinced they know what they're seeing. These mysterious objects, which they call spiral nebulae, are simply clouds of gas and dust within our own Milky Way. Nothing more than cosmic weather patterns in our galactic neighborhood. They couldn't have been more wrong. What they were actually observing were entire galaxies, each containing hundreds of billions of stars, stretching across distances so vast that light itself takes millions of years to cross them. These weren't minor features in our cosmic backyard. They were entire universes in their own right. Island cities of stars floating in the infinite darkness of space. But here's the truly mind-bending part. This wasn't just a small mistake made by a few astronomers. This was a fundamental misunderstanding that persisted for decades, embraced by virtually every major scientist of the era. Even Albert Einstein, whose theories would eventually help us understand the expanding universe, initially believed these spiral nebulae were local phenomena. How did we get it so spectacularly wrong? And more importantly, how did we finally discover the truth that would forever change our understanding of our place in the cosmos? The story begins in the late 1700s, when astronomers first started cataloguing these mysterious fuzzy patches in the night sky. William Herschel, the same astronomer who discovered Uranus, was among the first to systematically study these objects. He called them nebulae, from the Latin word for cloud, because that's exactly what they looked like through his telescopes. Cosmic clouds drifting through space. For over a century, this seemed perfectly reasonable. After all, we knew that our Milky Way contained plenty of gas and dust clouds. We could see them with our own eyes as dark patches silhouetted against the bright band of the Milky Way. So when astronomers spotted these spiral-shaped nebulae, it made perfect sense to assume they were simply more elaborate versions of the same phenomenon. But there were clues that something wasn't quite right with this picture. Some of these spiral nebulae were incredibly well organized, with elegant sweeping arms that seemed far too structured for simple gas clouds. Others appeared to contain what looked suspiciously like individual stars, though the telescopes of the time couldn't resolve them clearly enough to be certain. The real problem was one of scale. The universe that astronomers imagined in the early 1900s was a cozy, intimate place. They believed the Milky Way was essentially the entire universe, with everything else being minor decorations within it. The idea that there might be other galaxies, other island universes comparable to our own, was so radical that it barely occurred to anyone. This cosmic claustrophobia wasn't born out of ignorance, but rather from the limitations of the technology available at the time. The telescopes of the early 20th century, while revolutionary for their era, simply couldn't peer deep enough into space to reveal the true nature of these distant objects. It was like trying to understand the architecture of a city while looking at it through a fog so thick you could barely make out the shapes of buildings. The scientific establishment had constructed an entire framework of understanding based on this limited view. Textbooks were written, theories were developed, and careers were built on the assumption that these spiral nebulae were local phenomena. The idea that they might be something far more extraordinary, entire galaxies containing billions of stars, was relegated to the realm of speculation. But science has a way of correcting itself, often through the work of individuals who dare to question the established wisdom. In this case, the hero of our story is a soft-spoken astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California during the 1920s. Hubble had access to what was then the most powerful telescope in the world, the 100-inch Hooker telescope. This massive instrument could gather more light than any telescope before it, allowing astronomers to peer deeper into space than ever before. But having a powerful telescope is only half the battle. You also need to know how to use it effectively. What Hubble did was focus his attention on the Andromeda Nebula, one of the largest and brightest of the spiral nebulae. Night after night, he would point the great telescope toward this mysterious object, taking photograph after photograph, building up a detailed record of its structure. And then, on a fateful night in 1923, Hubble made a discovery that would shatter our understanding of the universe. Deep within the Andromeda Nebula, he spotted something that shouldn't have been there if it were simply a gas cloud in our own galaxy. He had found individual stars. Not just any stars, but a very special type of star called a Cepheid variable. These stars pulse with a regular rhythm, growing brighter and dimmer in a predictable pattern. More importantly, astronomers had already figured out that there's a direct relationship between how fast a Cepheid variable pulses and how bright it actually is. This discovery was like finding a cosmic ruler. By measuring how fast these Cepheid variables were pulsing, Hubble could determine their actual brightness. Then, by comparing their actual brightness to how bright they appeared through his telescope, he could calculate exactly how far away they were. The results were staggering. The Andromeda Nebula wasn't a nearby gas cloud at all. It was located nearly 1 million light-years away, far beyond the boundaries of our own Milky Way. And if it contained individual stars at that incredible distance, it couldn't be a simple nebula. It had to be an entire galaxy, comparable in size to our own. But Hubble didn't stop there. He began studying other spiral nebulae, finding Cepheid variables in many of them. Each discovery pushed the boundaries of the known universe further and further outward. What had once seemed like a collection of local gas clouds was revealed to be a vast population of distant galaxies, each containing billions of stars. The implications were profound and unsettling. If these were truly separate galaxies, then the universe was incomprehensibly larger than anyone had imagined. Our Milky Way, which had seemed like the entire cosmos, was suddenly reduced to just one galaxy among countless others scattered throughout an infinite expanse of space. This wasn't just a scientific discovery, it was a philosophical revolution. Humanity had to grapple with the realization that we weren't living at the center of creation, but rather on a small planet, orbiting an ordinary star in one galaxy among billions. It was a humbling moment that forced us to reconsider our place in the cosmic order. The scientific community initially resisted these findings. The idea that the universe could be so vast seemed almost too extraordinary to accept. Debates raged in scientific journals and at astronomical conferences. Some astronomers argued that Hubble's measurements must be wrong, that there had to be some other explanation for what he was seeing. But as more evidence accumulated, the truth became undeniable. The spiral nebulae were indeed distant galaxies, and the universe was far larger and more complex than anyone had dared to imagine. What had begun as a simple attempt to classify some fuzzy objects in the night sky had led to one of the most profound discoveries in the history of science. This revelation opened up entirely new questions about the nature of the universe. If there were billions of other galaxies out there, What did that mean for our understanding of cosmic evolution? How did these galaxies form? How were they distributed throughout space? And perhaps most intriguingly, were there other worlds like Earth-orbiting stars in these distant island universes? The discovery that spiral nebulae were actually galaxies also revealed something important about the nature of scientific progress. Sometimes our biggest breakthroughs come not from developing new theories, but from questioning our most basic assumptions. The astronomers of the early 1900s weren't stupid or incompetent. They were working with the best tools and knowledge available to them, but they had made a fundamental assumption about the scale of the universe that turned out to be completely wrong. This pattern repeats throughout the history of science. We build our understanding based on the evidence available to us, but sometimes that evidence is incomplete or misleading. It takes courage to question established wisdom, especially when that wisdom seems to be supported by decades of careful observation and measurement. Hubble's discovery also highlighted the crucial role that technology plays in advancing our understanding of the cosmos. The 100-inch telescope at Mount Wilson wasn't just a bigger version of earlier instruments, it represented a quantum leap in our ability to peer into the depths of space. Without this technological advancement, the true nature of galaxies might have remained hidden for decades longer. But perhaps the most remarkable aspect of this story is how it continues to unfold. Hubble's discovery that spiral nebulae were distant galaxies was just the beginning. As astronomers continued to study these objects with ever more powerful instruments, they uncovered layer after layer of cosmic complexity. We learned that galaxies come in many different shapes and sizes, from elegant spirals like our own Milky Way to massive elliptical galaxies containing trillions of stars. We discovered that galaxies are not randomly scattered through space, but are organized into clusters and superclusters, forming a vast cosmic web that stretches across the observable universe. We found that galaxies are not static objects, but dynamic systems that evolve over billions of years. They merge with each other, form new stars, and sometimes host explosive phenomena that can be seen across vast distances. We even discovered that most galaxies harbor supermassive black holes at their centers, objects so dense that not even light can escape their gravitational pull. Each new discovery built upon Hubble's fundamental insight that the universe is far larger and more complex than we had ever imagined. The spiral nebulae that had once seemed like minor curiosities in our cosmic neighborhood were revealed to be the building blocks of the entire observable universe. This transformation in our understanding didn't happen overnight. It took decades of careful observation, measurement, and theoretical work to fully appreciate the implications of Hubble's discovery. Even today, nearly a century later, we're still learning new things about the nature and behavior of galaxies. The story of how we misunderstood galaxies for so long serves as a powerful reminder of the importance of keeping an open mind in science. It's easy to become attached to our current understanding of the world, especially when that understanding has been carefully constructed over many years. But the history of science is filled with examples of revolutionary discoveries that overturned established wisdom. As we continue to push the boundaries of our cosmic knowledge with new telescopes and technologies, we must remember that our current understanding of the universe, no matter how sophisticated it might seem, is still incomplete. There are undoubtedly more surprises waiting to be discovered, more assumptions to be questioned, and more revolutionary insights to be gained. The galaxies that once confused our ancestors continue to hold secrets that we're only beginning to unravel. And in the next part of our journey, we'll explore how this fundamental misunderstanding about the nature of galaxies led to even more profound discoveries about the expanding universe and our place within it. The story of our galactic misunderstanding reveals something profound about human nature itself. We have this remarkable tendency to assume that what we can see represents the entirety of what exists. It's a cognitive bias that extends far beyond astronomy. But nowhere is it more beautifully illustrated than in our century-long confusion about the true nature of galaxies. Think about it this way. Imagine you're standing in the middle of a vast city at night, but you can only see clearly for about a block in any direction. Beyond that, everything becomes fuzzy and indistinct. You might spot some lights in the distance, but you can't tell if they're streetlights on the next block or entire neighborhoods miles away. That's essentially the situation astronomers found themselves in during the early 1900s. The Milky Way was their neighborhood, and everything else was just mysterious lights in the cosmic fog. It seemed perfectly reasonable to assume that these fuzzy spiral shapes were simply part of the same local environment. After all, why would nature create something as vast and complex as an entire galaxy when simpler explanations seem to work just fine? But here's where the story takes an even more fascinating turn. Even as Hubble was making his groundbreaking discoveries, he was uncovering evidence for something even more revolutionary. These distant galaxies weren't just sitting peacefully in space. They were moving. And not just moving randomly, but moving in a very specific pattern that would soon reveal one of the most profound truths about the universe itself. You see, when Hubble examined the light coming from these distant galaxies, he noticed something peculiar. The light was shifted toward the red end of the spectrum, a phenomenon known as redshift. This wasn't just a minor technical detail. It was a clue that would lead to one of the most important discoveries in the history of cosmology. To understand why this was so significant, we need to think about how light behaves when its source is moving. You've probably experienced this with sound waves. When an ambulance approaches you, its siren sounds higher in pitch, and when it moves away, the pitch drops. This is called the Doppler effect, and it happens with light waves too. If a galaxy is moving away from us, its light gets stretched out, shifting toward the red end of the spectrum. If it's moving toward us, the light gets compressed, shifting toward the blue end. When Hubble looked at these distant galaxies, he found that almost all of them were redshifted, meaning they were moving away from us. But that wasn't the most shocking part. What really blew his mind was that the more distant a galaxy was, the faster it appeared to be moving away. This wasn't what you'd expect if galaxies were just randomly drifting through space. It suggested something far more extraordinary. The universe itself was expanding. Imagine dots painted on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot, and the farther apart two dots are, the faster they separate. That's essentially what Hubble was seeing on a cosmic scale. Space itself was stretching, carrying galaxies along with it like dots on an expanding balloon. This discovery was so revolutionary that even Einstein initially refused to believe it. He had developed his theory of general relativity based on the assumption that the universe was static and unchanging. The idea that space itself could be expanding was so radical that he had actually added a mathematical term to his equations specifically to prevent this from happening. But Hubble's observations were undeniable. The evidence was right there in the light from distant galaxies, written in the language of redshift. The universe wasn't static, it was dynamic, evolving, expanding. And if it was expanding now, that meant it must have been smaller in the past, much smaller. This realization led to one of the most profound insights in human history. The universe had a beginning. If you could run the cosmic expansion backward like a movie in reverse, you'd find that everything in the universe was once compressed into an incredibly hot, dense state. This moment of cosmic birth would later become known as the Big Bang. The implications were staggering. Not only were we living in a universe filled with billions of galaxies, but that universe itself was evolving, expanding, and had emerged from a singular moment of creation, roughly 13.8 billion years ago. Our entire cosmic perspective had been turned upside down in the span of just a few decades. But the story doesn't end there. As astronomers continued to study these distant galaxies, with increasingly sophisticated instruments, they began to uncover even more surprising truths about the nature of the universe. They discovered that galaxies weren't just random collections of stars, but complex systems with their own internal structure and dynamics. They found that spiral galaxies like our own Milky Way have massive central bulges surrounded by thin disks of stars and gas. The spiral arms that had so puzzled earlier astronomers turned out to be density waves, regions where stars and gas bunch up temporarily before spreading out again. These aren't permanent structures, but rather patterns that sweep around the galaxy like waves on a pond. Elliptical galaxies, on the other hand, were revealed to be very different beasts altogether. These smooth, featureless systems contain mostly older, redder stars and very little gas for forming new ones. Many of them appear to be the products of galactic mergers, where two or more spiral galaxies have collided and merged into a single larger system. And then there were the irregular galaxies, chaotic, asymmetrical systems that didn't fit neatly into either category. These turned out to be particularly interesting because they often showed signs of intense star formation, creating brilliant regions of hot, young stars that could be seen across vast distances. As our understanding of galactic diversity grew, so did our appreciation for the incredible complexity of the universe. Each galaxy was like a city with its own unique history, architecture, and population. Some were ancient metropolises filled with old red stars, while others were vibrant young systems blazing with the light of newly formed stellar residents. The technology that made these discoveries possible was advancing at a breathtaking pace. The photographic plates that Hubble had used to capture images of distant galaxies were replaced by electronic detectors that could record far more detailed information. Radio telescopes revealed that galaxies emit not just visible light, but radio waves, X-rays, and other forms of radiation that told their own stories about the physics occurring within these systems. Space-based telescopes, freed from the blurring effects of Earth's atmosphere, began to reveal galactic structures in unprecedented detail. The Hubble Space Telescope, named after the astronomer who had first revealed the true nature of galaxies, could peer so deeply into space that it was actually looking back in time, showing us what galaxies looked like when the universe was much younger. What these observations revealed was astonishing. The early universe was a very different place from what we see today. Young galaxies were more chaotic, more active, and more prone to violent interactions. They were forming stars at rates that would be impossible in today's more mature universe. It was like watching the universe's wild teenage years compared to its current middle-age stability. But perhaps the most mind-bending discovery was yet to come. As astronomers studied the rotation of galaxies, they found something that didn't make sense. According to Newton's laws of motion, stars on the outer edges of galaxies should be moving more slowly than those near the center, just like planets in our solar system. But that's not what they observed. Instead, they found that stars throughout spiral galaxies were moving at roughly the same speed, regardless of their distance from the center. This was like discovering that Pluto orbits the Sun at the same speed as Mercury. It simply shouldn't be possible given the amount of visible matter in these systems. The only way to explain this observation was to assume that galaxies contained far more matter than we could see. This invisible matter, dubbed dark matter, appeared to outweigh all the visible stars and gas by a factor of 5 to 1. Suddenly, the galaxies we thought we understood were revealed to be dominated by a mysterious substance that we couldn't directly observe. This discovery opened up entirely new questions about the fundamental nature of the universe. What was this dark matter made of? How did it interact with ordinary matter? And if most of the universe was invisible, what other surprises might be waiting to be discovered? The search for dark matter became one of the most important quests in modern astronomy. Scientists built increasingly sophisticated detectors, both on Earth and in space, trying to catch glimpses of these elusive particles. They developed new theoretical models to explain how dark matter might behave and interact with the visible universe. Meanwhile, observations of distant galaxies continued to reveal new layers of cosmic complexity. Astronomers discovered that galaxies weren't randomly distributed throughout space, but were organized into vast structures, clusters, superclusters, and filaments that stretched across hundreds of millions of light years. These structures formed a cosmic web that connected all the galaxies in the observable universe. Even more surprising was the discovery that the expansion of the universe wasn't slowing down, as everyone had expected, but was actually accelerating. This implied the existence of yet another mysterious component of the universe, dark energy, that was somehow pushing space itself apart at an ever-increasing rate. Our understanding of galaxies had evolved from simple gas clouds in our cosmic neighborhood to complex systems embedded in a vast, dynamic universe, dominated by invisible forces we barely understood. Each answer seemed to raise 10 new questions, pushing the boundaries of human knowledge ever further into the unknown. The story of our galactic misunderstanding is ultimately a story about the power of curiosity and the importance of questioning our assumptions. The astronomers of the early 1900s weren't wrong to think that spiral nebulae were local phenomena. They were working with the best evidence available to them. But they were willing to change their minds when new evidence emerged, and that willingness to revise our understanding is what drives scientific progress. Today, we're still discovering new things about galaxies and the universe they inhabit. New telescopes are revealing galaxies so distant that their light has been traveling toward us for over 13 billion years. We're seeing the universe when it was just a baby, watching the first galaxies form and evolve in the cosmic dawn. Each new discovery reminds us that the universe is far stranger and more wonderful than we ever imagined. The simple spiral nebulae that once puzzled our ancestors have become windows into the deepest mysteries of existence itself. And who knows what new revelations await us as we continue to push the boundaries of our cosmic understanding. The transformation of our cosmic worldview didn't happen in a single eureka moment. Instead, it unfolded like a slow-motion earthquake, with each new discovery sending tremors through the foundations of everything astronomers thought they knew. The scientific community in the 1920s, suddenly faced with the reality that their cozy, familiar universe had been replaced by something unimaginably vast and alien. But here's what makes this story even more fascinating. The resistance to change wasn't just about stubborn scientists clinging to old ideas. There were genuine technical challenges that made it difficult to accept Hubble's revolutionary findings. The distances he was measuring were so enormous that they pushed the limits of what seemed physically possible. When Hubble announced that the Andromeda Galaxy was nearly 1 million light-years away, he was essentially saying that light from this object had been traveling through space for almost 1 million years before reaching our telescopes. To put that in perspective, when that light began its journey, our early human ancestors were just beginning to use stone tools. The photons hitting Hubble's photographic plates had been racing through the void since before recorded history began. The sheer scale was almost incomprehensible. If you could somehow travel at the speed of light, it would take you 1 million years just to reach our nearest galactic neighbor. In a universe where the farthest planets in our solar system were measured in mere hours or days of light travel, the concept of millions of light years seemed almost fictional. Many astronomers struggled to wrap their minds around these distances. Some argued that Hubble's measurements must be wrong, that there had to be some unknown factor affecting the brightness of Cepheid variables at such extreme distances. Others suggested that perhaps light itself behaved differently over cosmic distances, making these calculations unreliable. The debate raged for years in scientific journals and at astronomical conferences. It wasn't just about numbers and measurements. It was about the very nature of reality itself. If Hubble was right, then humans were living in a universe so vast that it dwarfed every previous conception of cosmic scale. We weren't just inhabitants of a galaxy. We were citizens of one galaxy among billions, scattered throughout an infinite expanse of space and time. This philosophical upheaval extended far beyond the scientific community. Religious leaders grappled with the implications of a universe filled with countless other worlds. Philosophers debated what it meant for human significance if we were just one small part of an incomprehensibly large cosmic structure. Writers and artists began to explore themes of cosmic loneliness and wonder that had never before seemed relevant to human experience. But science has a way of settling debates through the accumulation of evidence, and the evidence for Hubble's interpretation kept mounting. Other astronomers began finding Cepheid variables in different spiral nebulae, each discovery confirming that these objects were indeed distant galaxies. The measurements became more precise, the techniques more refined, and the conclusions more inescapable. By the 1930s, the astronomical community had largely accepted the reality of other galaxies. What had once seemed like a radical proposal became established fact. Textbooks were rewritten, university courses were redesigned, and a new generation of astronomers began their careers with the understanding that the universe was filled with billions of island universes, each containing billions of stars. This acceptance opened up entirely new fields of research. Astronomers began studying the different types of galaxies, trying to understand why some were spirals, while others were elliptical or irregular. They investigated how galaxies formed, how they evolved over time, and how they interacted with each other across the vast distances of space. The technological revolution that made these discoveries possible was accelerating rapidly. New types of photographic emulsions could capture fainter objects and reveal more detail. Larger telescopes gathered more light, allowing astronomers to peer deeper into space than ever before. Spectroscopy techniques improved, making it possible to analyze the chemical composition and motion of distant galaxies with unprecedented precision. Each technological advance revealed new layers of galactic complexity. Astronomers discovered that galaxies weren't just collections of stars, but complex ecosystems containing gas, dust, magnetic fields, and high-energy particles. They found that some galaxies were actively forming new stars, while others seemed to have exhausted their stellar nurseries and were filled primarily with ancient dying stars. The diversity was staggering. Some galaxies were small and faint, containing only a few million stars. Others were massive giants with trillions of stellar residents. Some were perfectly symmetrical, while others showed signs of recent collisions or interactions with neighboring galaxies. Each system told its own unique story of cosmic evolution. As observations became more sophisticated, astronomers began to notice patterns in this galactic zoo. Spiral galaxies, like our own Milky Way, were most common in less crowded regions of space, where they could maintain their delicate structures without being disrupted by close encounters with neighbors. Elliptical galaxies, on the other hand, were often found in dense clusters where gravitational interactions were more frequent. These patterns suggested that environment played a crucial role in determining a galaxy's fate. Galaxies living in cosmic cities experienced different evolutionary pressures than those in more isolated cosmic suburbs. Some were stripped of their gas by interactions with hot intergalactic medium, while others were stretched and distorted by gravitational encounters with massive neighbors. The realization that galaxies were not isolated systems, but part of a larger cosmic ecosystem, was another profound shift in thinking. Just as Darwin had shown that species evolved in response to their environment, astronomers were discovering that galaxies evolved in response to their cosmic surroundings. The universe wasn't just vast, it was interconnected in ways that were only beginning to be understood. This interconnectedness became even more apparent as astronomers began mapping the three-dimensional distribution of galaxies throughout space. Using redshift measurements to determine distances, they could create maps showing where galaxies were located relative to each other. What they found was astonishing. Galaxies weren't randomly scattered throughout space, but were organized into vast structures that resembled a cosmic web. Long filaments of galaxies stretched across hundreds of millions of light years, connecting dense nodes where thousands of galaxies clustered together. Between these filaments lay enormous voids, regions of space that contained very few galaxies at all. The universe had structure on scales that boggled the mind, with patterns that repeated across cosmic distances. This cosmic web revealed something fundamental about how the universe had evolved since the Big Bang. The tiny fluctuations in density that existed in the early universe had grown over billions of years, with gravity pulling matter together into increasingly complex structures. Galaxies weren't just random collections of stars. They were the end products of cosmic evolution, shaped by forces operating on the largest scales imaginable. The discovery of this large-scale structure also raised new questions about the nature of matter itself. The visible galaxies represented only a small fraction of the total mass needed to explain the observed structures. Most of the universe seemed to be composed of invisible dark matter, which revealed itself only through its gravitational effects on visible matter. This dark matter wasn't just a minor correction to our understanding. It was a fundamental component of the cosmos that outweighed everything we could see by a factor of 5 to 1. The galaxies we had spent decades studying were merely the visible tips of massive dark matter icebergs, floating in an ocean of invisible material that dominated the universe's mass budget. The implications were staggering. If most of the universe was invisible, what did that say about our ability to understand the cosmos? How could we claim to comprehend the nature of reality when we couldn't even detect the majority of the matter around us? It was a humbling reminder that despite all our technological advances, we were still cosmic novices, struggling to understand forces and phenomena that operated on scales beyond our everyday experience. Yet rather than being discouraged by these discoveries, astronomers embraced them as new frontiers to explore. The existence of dark matter opened up entirely new areas of research, from particle physics experiments designed to detect these elusive particles, to computer simulations that modeled how dark matter might have shaped the evolution of the universe. Space-based telescopes began to reveal galaxies in wavelengths of light that couldn't be seen from Earth's surface. Infrared observations showed star formation happening in dusty regions that had been hidden from optical telescopes. X-ray telescopes revealed the hot gas that filled the spaces between galaxies in clusters, heated to temperatures of millions of degrees by the gravitational energy of these massive systems. Each new wavelength of observation was like gaining a new sense, revealing aspects of galactic behavior that had been completely invisible before. Galaxies that appeared quiet and peaceful in visible light were revealed to be sites of violent activity when observed in radio waves or X-rays. Some harbored supermassive black holes that were actively consuming matter and blasting jets of high-energy particles across millions of light years. The universe was far more dynamic and energetic than anyone had imagined. Galaxies weren't just passive collections of stars drifting through space. They were complex, evolving systems engaged in constant interactions with their environment and with each other. They grew by consuming smaller neighbors. They triggered bursts of star formation through gravitational encounters. And they were shaped by processes operating on both the smallest and largest scales in the universe. This dynamic view of galaxies also revealed something profound about the nature of time in the universe. Because light takes time to travel across cosmic distances, looking at distant galaxies meant looking back in time. The farther away a galaxy was, the younger it appeared, showing us what galaxies looked like when the universe was in its infancy. These observations revealed that the early universe was a very different place from the cosmos we see today. Young galaxies were more chaotic, more active, and more prone to violent interactions. They were forming stars at rates that would be impossible in the present-day universe, creating brilliant regions of hot, young stars that blazed across cosmic distances. As astronomers pushed their observations to ever greater distances, they began to see galaxies as they existed when the universe was only a few 100 million years old. These ancient systems were smaller, more irregular, and more actively star-forming than their modern counterparts. They were the building blocks from which today's massive galaxies had been assembled through billions of years of cosmic evolution. The story of galactic evolution became a story about the universe itself, revealing how cosmic structures had grown from tiny seeds in the early universe into the vast, complex systems we observe today. Each galaxy was like a fossil record, preserving information about the conditions that existed when it formed and the processes that had shaped it over cosmic time. This historical perspective transformed our understanding of our own place in the cosmos. The Milky Way wasn't just our current home, it was the product of billions of years of cosmic evolution, assembled from smaller galaxies that had merged and grown over time. The very atoms in our bodies had been forged in the hearts of stars that had lived and died in galaxies that no longer existed, their material eventually finding its way into the spiral system we call home. The realization that we were not just inhabitants of a galaxy, but products of galactic evolution, created a profound sense of cosmic connection. We weren't separate from the universe, we were part of it, made from the same materials, and shaped by the same forces that had created the vast structures we observed in the night sky. This connection became even more meaningful as astronomers began to understand the role that galaxies play in creating the conditions necessary for life. The heavy elements essential for rocky planets and biological processes were forged in the hearts of massive stars and distributed throughout galaxies by supernova explosions. The spiral arms of galaxies like our own created regions of enhanced star formation, where new solar systems could emerge from the enriched material of previous stellar generations. Without galaxies, there would be no stars, no planets, and no life. These vast cosmic structures weren't just beautiful objects to admire through telescopes. They were the fundamental organizing principles of the universe, the frameworks within which all the complexity and beauty of the cosmos could emerge. The journey from viewing spiral nebulae as local gas clouds to understanding them as vast galactic cities represents one of the most profound shifts in human perspective in the history of science. It revealed not just the true scale of the universe, but our intimate connection to cosmic processes that operate on scales both vast and intimate. As we continue to probe deeper into the nature of galaxies with ever more sophisticated instruments, we're still discovering new aspects of these cosmic leviathans that challenge our understanding. Each new observation adds another piece to the puzzle, revealing the universe to be even more complex, more beautiful, and more interconnected than we ever imagined. The story of our galactic misunderstanding reveals something even more fascinating about the nature of scientific discovery itself. Sometimes the most revolutionary insights come not from finding something new, but from realizing that something we've been staring at for decades is completely different from what we thought it was. Consider the psychological challenge that confronted astronomers in the 1920s. They had built their entire careers on a certain understanding of the universe's scale and structure. They had written papers, taught students, and constructed theoretical frameworks, all based on the assumption that these spiral nebulae were local phenomena. Suddenly, they were being asked to accept that everything they thought they knew about the cosmos was fundamentally wrong. It's a bit like discovering that what you thought was a small pond in your backyard is actually a vast ocean stretching to the horizon. The adjustment isn't just intellectual, it's deeply emotional and philosophical. Many astronomers struggled with the implications of Hubble's discoveries, not because they were scientifically invalid, but because they were so overwhelming that they challenged the very foundations of human cosmic significance. Some scientists clung to alternative explanations for as long as possible. They proposed that perhaps there was some unknown form of cosmic dust that was making distant objects appear fainter than they actually were, throwing off distance calculations. Others suggested that the laws of physics might work differently over such vast scales, making standard measurement techniques unreliable. These weren't unreasonable concerns. After all, Hubble was extrapolating from observations of nearby Cepheid variables to make claims about objects millions of times more distant. The leap in scale was so enormous that it stretched the limits of what seemed scientifically justifiable. It was like using a ruler to measure the distance to another continent, technically possible, but requiring a chain of assumptions that made many scientists uncomfortable. But the beauty of science lies in its self-correcting nature. As more astronomers began studying these distant objects with increasingly sophisticated techniques, the evidence for their extragalactic nature became overwhelming. Independent measurements using different methods all pointed to the same conclusion. These spiral nebulae were indeed separate galaxies, located at distances that dwarfed anything previously imagined. The psychological impact of this revelation extended far beyond the scientific community. Popular magazines began publishing articles about the island universe theory, introducing the general public to the concept of a cosmos filled with billions of other galaxies. Science fiction writers seized on these ideas, creating stories about interstellar travel and alien civilizations that might exist in these distant stellar cities. Religious leaders found themselves grappling with theological implications they had never considered. If the universe contained billions of other worlds, what did that mean for humanity's special place in creation? Some embraced the discovery as evidence of divine grandeur on an unimaginable scale, while others worried about the implications for traditional beliefs about human uniqueness. The transformation of our cosmic worldview also had profound implications for how we understood our own planet and solar system. Earth was no longer the center of a cozy universe, but a tiny speck orbiting an ordinary star in one galaxy among billions. This realization was both humbling and inspiring, challenging humans to think about their place in the cosmos in entirely new ways. But perhaps the most remarkable aspect of this story is how it illustrates the power of technology to transform our understanding of reality. The 100-inch Hooker telescope that Hubble used wasn't just a bigger version of earlier instruments. It represented a quantum leap in our ability to gather and analyze light from distant objects. Without this technological breakthrough, the true nature of galaxies might have remained hidden for decades longer. The lesson here is that our understanding of the universe is always limited by the tools we have available to study it. Each new generation of telescopes, detectors, and analytical techniques reveals aspects of the cosmos that were previously invisible. What seems like established fact today might be overturned tomorrow by observations that push the boundaries of what we can detect and measure. This principle has continued to drive astronomical discovery throughout the decades since Hubble's groundbreaking work. Radio telescopes revealed that many galaxies emit powerful radio waves, suggesting the presence of phenomena that couldn't be detected in visible light. Space-based observatories freed from the blurring effects of Earth's atmosphere began to show galactic structures in unprecedented detail. Each new observational capability revealed additional layers of complexity in galactic behavior. Astronomers discovered that galaxies weren't just collections of stars, but complex ecosystems containing vast amounts of gas, dust, and mysterious dark matter. They found that some galaxies were actively forming new stars, while others had exhausted their stellar nurseries and were slowly fading away. The diversity of galactic types became even more apparent as observations improved. Spiral galaxies like our own Milky Way were revealed to have intricate structures, with density waves creating the beautiful spiral arms that had first caught astronomers' attention. Elliptical galaxies turned out to be smooth, featureless systems that often showed evidence of having formed through the merger of smaller galaxies. But perhaps the most surprising discovery was that galaxies weren't isolated systems drifting independently through space. Instead, they were part of a vast cosmic web of structure that connected them across enormous distances. Galaxies clustered together in groups and clusters, which in turn were connected by filaments of dark matter that stretched across hundreds of millions of light years. This cosmic web revealed something fundamental about how the universe had evolved since the Big Bang. The tiny fluctuations in density that existed in the early universe had grown over billions of years, with gravity pulling matter together into increasingly complex structures. The galaxies we see today are the end products of this cosmic evolution, shaped by forces operating on the largest scales imaginable. The discovery of large-scale structure also highlighted the importance of dark matter in shaping the universe we observe. This invisible substance, which outweighs all visible matter by a factor of 5 to 1, provides the gravitational scaffolding that holds galaxies and galaxy clusters together. Without dark matter, the structures we see in the universe today could never have formed. Understanding the role of dark matter required astronomers to completely rethink their approach to studying galaxies. They could no longer focus solely on the stars and gas they could see, but had to consider the invisible halos of dark matter that dominated each galaxy's mass. This led to new techniques for mapping dark matter distributions and understanding how they influence galactic evolution. The story of galactic discovery also illustrates how scientific progress often requires collaboration across different disciplines and institutions. Hubble's breakthrough was built on the work of countless other astronomers who had catalogued nebulae, calibrated distance indicators, and developed the theoretical frameworks needed to interpret observations. Science is ultimately a collective enterprise, with each discovery building on the insights of previous generations. As our understanding of galaxies deepened, it became clear that these cosmic structures play a crucial role in creating the conditions necessary for life. The heavy elements essential for rocky planets and biological processes are forged in the hearts of massive stars and distributed throughout galaxies by supernova explosions. The spiral arms of galaxies like our own create regions of enhanced star formation, where new solar systems can emerge from the enriched material of previous stellar generations. This connection between galactic evolution and the possibility of life added a new dimension to astronomical research. Astronomers began studying how different types of galaxies might support the development of planetary systems and the emergence of life. They investigated how galactic mergers, supernova explosions, and other cosmic events might influence the habitability of worlds within these systems. The realization that we are not just inhabitants of a galaxy, but products of galactic evolution, created a profound sense of cosmic connection. The atoms in our bodies were forged in stellar cores that existed billions of years ago, in galaxies that may no longer exist in their original form. We are literally made of star stuff, connected to the cosmos in ways that our ancestors could never have imagined. This perspective has continued to evolve as astronomers push their observations to ever greater distances and earlier times in cosmic history. By looking at the most distant galaxies, they are seeing these systems as they existed when the universe was young, revealing how galactic structures have evolved over billions of years. These observations have shown that the early universe was a very different place from the cosmos we see today. Young galaxies were more chaotic, more actively star-forming, and more prone to violent interactions. They were smaller and more irregular than their modern counterparts, representing the building blocks from which today's massive galaxies were assembled. The study of galactic evolution has also revealed the dynamic nature of the universe itself. Galaxies are not static objects, but constantly changing systems that grow through mergers, evolve through star formation, and interact with their environment in complex ways. The universe is not a fixed stage upon which cosmic drama unfolds, but an active participant in the evolutionary process. This dynamic view of the cosmos has profound implications for our understanding of our place within it. We are not observers standing outside the universe looking in, but participants in an ongoing cosmic story that began with the Big Bang and continues to unfold today. Our existence is intimately connected to the processes that have shaped galaxies over billions of years. The journey from viewing spiral nebulae as local gas clouds to understanding them as vast galactic cities represents more than just a scientific revolution. It represents a fundamental shift in human consciousness. It forced us to expand our conception of reality to encompass scales of space and time that challenge our ability to comprehend them. Yet even as we've gained this cosmic perspective, new mysteries have emerged that remind us how much we still don't understand. The discovery of dark matter and dark energy has revealed that the universe is dominated by invisible components that we can barely detect, let alone comprehend. The nature of these mysterious substances remains one of the greatest challenges in modern astronomy. The story of our galactic misunderstanding also serves as a powerful reminder of the importance of maintaining intellectual humility in the face of the unknown. The astronomers of the early 1900s weren't ignorant or incompetent. They were working with the best evidence available to them and drawing reasonable conclusions based on that evidence. Their mistake was not in their observations or reasoning, but in their assumptions about the scale and nature of the universe. This lesson remains relevant today as we continue to push the boundaries of our cosmic understanding. Our current theories about galaxies, dark matter, and the evolution of the universe are based on the best evidence available to us, but they may well be overturned by future discoveries that reveal aspects of reality we cannot currently detect or imagine. The continuing evolution of our galactic understanding demonstrates that science is not a destination but a journey, a process of gradually refining our picture of reality through careful observation, experimentation, and theoretical development. Each new discovery adds another piece to the cosmic puzzle, but also reveals new questions that challenge our assumptions and push us to look deeper. As we stand on the threshold of a new era in astronomical observation, with space-based telescopes capable of detecting the most distant galaxies in the universe, and ground-based instruments that can peer through cosmic dust to reveal hidden galactic structures, we can be certain that more surprises await us. The story of how we misunderstood galaxies for so long is far from over. It's simply the first chapter in an ongoing adventure of cosmic discovery that will continue as long as humans look up at the night sky and wonder about their place in the vast tapestry of existence. The transformation of our understanding didn't happen overnight, and it didn't happen without resistance. But ultimately, the evidence spoke for itself, forcing even the most skeptical astronomers to accept that the universe was far stranger and more wonderful than they had ever imagined. In doing so, it opened up new frontiers of exploration that continue to challenge and inspire us today. As we delve deeper into this cosmic detective story, we encounter perhaps the most fascinating aspect of how galaxies were misunderstood: the role that our own position in the universe played in obscuring the truth. You see, we weren't just dealing with limitations in technology or observational techniques. We were grappling with the fundamental challenge of trying to understand the cosmos from within it. Imagine trying to understand the layout of a vast city while standing in the middle of it on a foggy night. You can see the buildings immediately around you clearly enough, but everything beyond a certain distance becomes increasingly fuzzy and indistinct. That's essentially the predicament that early astronomers found themselves in when trying to make sense of the universe's structure. The Milky Way, our galactic home, presented both an opportunity and a profound obstacle to understanding the true nature of other galaxies. On one hand, we could study its structure in detail, observing individual stars, gas clouds, and stellar formations with remarkable precision. On the other hand, we were embedded so deeply within it that we couldn't step back and see the bigger picture. This is where the story takes another intriguing turn. Even as Hubble was revolutionizing our understanding of distant galaxies, astronomers were still struggling to comprehend the basic structure of our own cosmic neighborhood. They knew the Milky Way was a flattened, disc-like system with a central bulge, but they had no idea how truly massive it was or what it might look like from the outside. The breakthrough came when astronomers began to realize that if other spiral nebulae were indeed distant galaxies, then our own Milky Way must be a spiral galaxy too. This was a profound conceptual leap. The idea that we were living inside one of these beautiful, symmetrical structures that we had been admiring from afar. But confirming this hypothesis proved to be extraordinarily difficult. How do you map the structure of a galaxy when you're embedded within it? It's like trying to understand the shape of a forest while standing among the trees. Every direction you look, your view is blocked by nearby stars and clouds of interstellar dust. The solution required astronomers to become cosmic archaeologists, piecing together clues from across the electromagnetic spectrum. They studied the distribution of different types of stars, traced the paths of gas clouds, and mapped the locations of stellar nurseries where new stars were being born. Slowly, painstakingly, they began to construct a picture of the Milky Way's spiral structure. What they discovered was both humbling and awe-inspiring. Not only were we living inside a spiral galaxy, but we were located in one of its spiral arms, roughly halfway between the center and the edge. Our entire solar system, with all its planets and moons, was just a tiny speck in one small corner of this vast stellar city. This realization added another layer of complexity to the story of galactic misunderstanding. For centuries, humans had assumed they occupied a special, central position in the universe. First, we had to accept that Earth wasn't the center of the solar system. Then, we learned that the Sun wasn't the center of the galaxy. Now, we were discovering that our galaxy wasn't even the center of the universe. It was just one of countless others scattered throughout infinite space. Each of these revelations represented a fundamental shift in human perspective, what astronomers call the principle of cosmic mediocrity. Rather than occupying a privileged position in the cosmos, we were beginning to understand that we lived in a perfectly ordinary location, a typical planet orbiting a typical star in a typical galaxy floating in the vast ocean of space. But this apparent ordinariness was actually quite extraordinary when you thought about it carefully. The fact that we existed at all in a universe capable of supporting the complex chemistry necessary for life was itself a kind of miracle. The conditions that allowed galaxies to form, stars to ignite, and planets to develop were incredibly specific and delicate. As astronomers continued to study galactic structure and evolution, they began to appreciate just how finely tuned the universe had to be for any of this to be possible. If the fundamental forces of nature had been even slightly different, galaxies might never have formed at all. If the expansion rate of the universe had been too fast or too slow, matter would never have been able to clump together into the structures we observe today. This led to what became known as the fine-tuning problem in cosmology. The universe seemed to be calibrated with extraordinary precision to allow for the existence of galaxies, stars, planets, and ultimately life itself. Some scientists saw this as evidence of design or purpose in the cosmos, while others proposed that we might be living in just one of countless universes, each with different physical laws and constants. The debate over cosmic fine-tuning revealed something important about the nature of scientific inquiry itself. Even as we gained unprecedented knowledge about the structure and evolution of galaxies, we were confronted with deeper questions about why the universe was the way it was. Each answer seemed to generate new mysteries that pushed the boundaries of human understanding even further. Meanwhile, the technology for studying galaxies continued to advance at a breathtaking pace. New types of telescopes could observe different wavelengths of light, revealing aspects of galactic behavior that had been completely invisible before. Radio telescopes showed that many galaxies were emitting powerful radio waves, suggesting the presence of exotic phenomena like supermassive black holes and high-energy particle jets. Infrared telescopes could peer through the dust that obscured much of the visible light from distant galaxies, revealing star formation happening in regions that had been hidden from optical observations. X-ray telescopes detected the hot gas that filled the spaces between galaxies in clusters, heated to temperatures of millions of degrees by the gravitational energy of these massive systems. Each new wavelength of observation was like gaining a new sense, revealing aspects of galactic behavior that challenged existing theories and models. Galaxies that appeared quiet and peaceful in visible light were revealed to be sites of violent activity when observed in radio waves or X-rays. Some harbored supermassive black holes that were actively consuming matter and blasting jets of high-energy particles across millions of light years. The universe was turning out to be far more dynamic and energetic than anyone had imagined. Galaxies weren't just passive collections of stars drifting through space. They were complex, evolving systems engaged in constant interactions with their environment and with each other. They grew by consuming smaller neighbors, triggered bursts of star formation through gravitational encounters, and were shaped by processes operating on both the smallest and largest scales imaginable. This dynamic view of galaxies also revealed something profound about the nature of time in the universe. Because light takes time to travel across cosmic distances, looking at distant galaxies meant looking back in time. The farther away a galaxy was, the younger it appeared, showing us what these systems looked like when the universe was in its infancy. These observations revealed that the early universe was a very different place from the cosmos we see today. Young galaxies were more chaotic, more active, and more prone to violent interactions. They were forming stars at rates that would be impossible in the present-day universe, creating brilliant regions of hot, young stars that blazed across cosmic distances. As astronomers pushed their observations to ever greater distances, they began to see galaxies as they existed when the universe was only a few 100 million years old. These ancient systems were smaller, more irregular, and more actively star-forming than their modern counterparts. They were the building blocks from which today's massive galaxies had been assembled through billions of years of cosmic evolution. The story of galactic evolution became inseparable from the story of the universe itself. Each galaxy was like a time capsule, preserving information about the conditions that existed when it formed and the processes that had shaped it over cosmic history. By studying galaxies at different distances and ages, astronomers could piece together a coherent picture of how the universe had evolved from its initial state to its current configuration. This historical perspective transformed our understanding of our own place in the cosmos. The Milky Way wasn't just our current home, it was the product of billions of years of cosmic evolution, assembled from smaller galaxies that had merged and grown over time. The very atoms in our bodies had been forged in the hearts of stars that had lived and died in previous generations of galaxies, their material eventually finding its way into the spiral system we call home. The realization that we were not just inhabitants of a galaxy, but products of galactic evolution, created a profound sense of cosmic connection. We weren't separate from the universe, we were part of it, made from the same materials and shaped by the same forces that had created the vast structures we observed in the night sky. This connection became even more meaningful as astronomers began to understand the role that galaxies play in creating the conditions necessary for life. The heavy elements essential for rocky planets and biological processes were forged in the hearts of massive stars and distributed throughout galaxies by supernova explosions. The spiral arms of galaxies like our own created regions of enhanced star formation, where new solar systems could emerge from the enriched material of previous stellar generations. Without galaxies, there would be no stars, no planets, and no life. These vast cosmic structures weren't just beautiful objects to admire through telescopes. They were the fundamental organizing principles of the universe, the frameworks within which all the complexity and beauty of the cosmos could emerge. The journey from viewing spiral nebulae as local gas clouds to understanding them as vast galactic cities represents one of the most profound shifts in human perspective in the history of science. It revealed not just the true scale of the universe, but our intimate connection to cosmic processes that operate on scales both vast and intimate. Yet even as we've gained this cosmic perspective, new mysteries have emerged that remind us how much we still don't understand. The discovery of dark matter revealed that most of the universe is invisible, composed of mysterious particles that we can barely detect. The realization that cosmic expansion is accelerating pointed to the existence of dark energy, an even more enigmatic force that seems to be pushing the universe apart at an ever-increasing rate. These discoveries have forced astronomers to confront the humbling reality that the universe we can see and study directly represents only a tiny fraction of what actually exists. The galaxies that had seemed so substantial and permanent are now understood to be merely the visible peaks of massive dark matter mountains, floating in an ocean of invisible energy that dominates the cosmos. The story of our galactic misunderstanding thus becomes a meditation on the nature of knowledge itself. How can we claim to understand the universe when we're aware that most of it is invisible to us? How do we construct reliable theories about cosmic evolution when we're missing crucial pieces of the puzzle? These questions don't have easy answers, but they point to something beautiful about the scientific enterprise. Science isn't about achieving perfect knowledge. It's about constantly refining our understanding through careful observation, experimentation, and theoretical development. Each new discovery adds another piece to the cosmic puzzle, but also reveals new questions that challenge our assumptions and push us to look deeper. The continuing evolution of our galactic understanding demonstrates that science is not a destination, but a journey, a process of gradually approaching truth through the accumulation of evidence and the refinement of ideas. What seemed like established fact to one generation of astronomers becomes the launching point for new discoveries by the next. As we stand on the threshold of a new era in astronomical observation, with space-based telescopes capable of detecting the most distant galaxies in the universe and ground-based instruments that can peer through cosmic dust to reveal hidden galactic structures, we can be certain that more surprises await us. The story of how we misunderstood galaxies for so long is far from over. It's simply the first chapter in an ongoing adventure of cosmic discovery. The transformation of our cosmic worldview from the early 1900s to today represents more than just a scientific revolution. It represents a fundamental expansion of human consciousness. We've learned to think on scales of space and time that challenge our ability to comprehend them, to see ourselves as part of a vast, evolving cosmos, rather than observers standing outside it. This expanded perspective has profound implications for how we understand our place in the universe and our responsibilities as conscious beings capable of contemplating the cosmos. We are not just products of galactic evolution. We are the universe becoming aware of itself, capable of studying its own history and structure through the tools of science and observation. The galaxies that once confused our ancestors continue to hold secrets that we're only beginning to unravel. Each new observation adds another layer to our understanding, revealing the universe to be even more complex, more beautiful, and more interconnected than we ever imagined. And as we continue to push the boundaries of our cosmic knowledge, we're reminded that the greatest discoveries often come not from finding something new, but from realizing that something we've been staring at for years is completely different from what we thought it was. The implications of Hubble's discovery rippled through every aspect of human understanding. But perhaps nowhere was the impact more profound than in our conception of time itself. When astronomers realized they were looking at galaxies millions of light years away, they weren't just measuring distance, they were peering into the past. Think about what this means for a moment. The light from the Andromeda galaxy that Edwin Hubble captured on his photographic plates in 1923 had been traveling through space for over 2 million years. When that light began its journey toward Earth, our earliest human ancestors were just learning to use primitive stone tools. The photons hitting Hubble's telescope had been racing through the void since before civilization, before agriculture, before written language existed. This realization transformed astronomy from a study of distant objects into a form of time travel. Every galaxy we observe exists in multiple moments simultaneously, as it was when its light left, and as it might be now, billions of years later. The universe became a vast archive of its own history, with each distant galaxy preserving a snapshot of cosmic conditions from a different era. But this temporal perspective created new puzzles that astronomers are still grappling with today. If we're seeing galaxies as they were millions or billions of years ago, how do we study their current state? How do we understand galactic evolution when we can only observe frozen moments from the past? The answer lies in what astronomers call the cosmic distance ladder, a series of increasingly sophisticated techniques for measuring distances to ever more remote objects. Each rung of this ladder builds upon the previous one, creating a chain of measurements that stretches from nearby stars to the edge of the observable universe. The foundation of this ladder rests on parallax measurements of nearby stars. Just as you can judge the distance to a nearby object by observing how it appears to shift position when you close one eye and then the other, astronomers can measure stellar distances by observing how stars appear to move against the background of more distant objects as Earth orbits the Sun. This technique only works for relatively nearby stars, but it provides the calibration for the next rung of the ladder: Cepheid variable stars, like the ones Hubble used to measure the distance to Andromeda. By studying Cepheids in nearby galaxies where we can also measure parallax distances, astronomers can refine their understanding of the relationship between these stars' pulsation periods and their actual brightness. For galaxies too distant to resolve individual Cepheid variables, astronomers developed new techniques using entire star clusters, supernovae, and even the properties of whole galaxies as distance indicators. Each method extends our reach further into space and deeper into time, revealing the universe's history in unprecedented detail. What emerged from these observations was a picture of cosmic evolution that no one had anticipated. The universe wasn't static and unchanging, as most astronomers had assumed. Instead, it was dynamic, evolving, with galaxies forming, merging, and transforming over billions of years. The spiral nebulae that had seemed so permanent and eternal were actually temporary configurations in an ever-changing cosmic dance. The early universe, astronomers discovered, was a much more violent and chaotic place than the relatively serene cosmos we observe today. Young galaxies were constantly colliding and merging, their interactions triggering massive bursts of star formation that illuminated the primordial darkness. These ancient stellar nurseries were far more active than anything we see in the modern universe, creating stars at rates that would quickly exhaust the available gas and dust. As these early galaxies evolved, they began to settle into the more orderly structures we observe today. The violent mergers that characterized the universe's youth became less frequent as cosmic expansion carried galaxies further apart. The frenzied star formation of the early epochs gave way to the more measured pace of stellar birth we see in contemporary galaxies. This evolutionary perspective revealed something profound about the nature of structure in the universe. The beautiful spiral arms that had first captured astronomers' attention weren't permanent features carved into the fabric of space, but rather temporary waves of enhanced star formation that swept around galactic disks like ripples on a pond. These density waves could persist for hundreds of millions of years, but they were ultimately transient phenomena in the longer story of galactic evolution. The realization that galactic structures were temporary challenged fundamental assumptions about the nature of cosmic order. If spiral arms could form and dissolve, if galaxies could merge and transform, then what did it mean to classify these objects into distinct types? Were elliptical and spiral galaxies truly different species, or were they simply different phases in a common evolutionary sequence? The answer, astronomers discovered, was both. While some galaxies maintain their basic structure for billions of years, others undergo dramatic transformations that can completely alter their appearance. A spiral galaxy that falls into a dense cluster of galaxies might have its spiral arms stripped away by gravitational interactions, transforming it into an elliptical system. Two spiral galaxies that collide and merge might create a single, larger elliptical galaxy from their combined material. This dynamic view of galactic evolution required astronomers to develop entirely new ways of thinking about these cosmic structures. Instead of seeing galaxies as fixed objects with unchanging properties, they began to understand them as complex systems with their own life cycles. Birth, growth, maturity, and in some cases, dramatic transformation or even death. The study of galactic evolution also revealed the crucial role that environment plays in determining a galaxy's fate. Galaxies living in the cosmic equivalent of dense urban centers experience very different evolutionary pressures than those in more isolated cosmic suburbs. The hot, thin gas that fills the space between galaxies and clusters can strip away the raw material needed for star formation, effectively sterilizing galaxies and preventing them from creating new stellar generations. Meanwhile, galaxies in less crowded regions of space can maintain their star-forming activity for much longer periods, continuing to create new stars from the gas and dust in their spiral arms. These environmental effects help explain why different types of galaxies are found in different cosmic neighborhoods, with elliptical galaxies more common in dense clusters and spiral galaxies more prevalent in less crowded regions. The recognition that galactic properties are influenced by environment was another blow to the idea that we could understand these systems in isolation. Just as biologists had learned that species evolve in response to their ecosystems, astronomers were discovering that galaxies evolve in response to their cosmic surroundings. The universe wasn't just a collection of independent objects, but a complex web of interactions operating on scales from individual stars to galaxy clusters. This interconnected view of the cosmos gained even more support as astronomers began to map the three-dimensional distribution of galaxies throughout space. Using redshift measurements to determine distances, they could create maps showing where galaxies were located relative to each other in 3 dimensions. What they found was astonishing. Galaxies weren't randomly scattered throughout space, but were organized into vast structures that resembled a cosmic web. Long filaments of galaxies stretched across hundreds of millions of light years, connecting dense nodes where thousands of galaxies clustered together. Between these filaments lay enormous voids, regions of space that contained very few galaxies at all. The universe had structure on scales that boggled the mind, with patterns that repeated across cosmic distances. This cosmic web revealed something fundamental about how the universe had evolved since the Big Bang. The tiny fluctuations in density that existed in the early universe had grown over billions of years, with gravity pulling matter together into increasingly complex structures. The galaxies we see today are the end products of this cosmic evolution, shaped by forces operating on the largest scales imaginable. The discovery of large-scale structure also raised profound questions about the nature of matter itself. The visible galaxies represented only a small fraction of the total mass needed to explain the observed structures. Computer simulations showed that the cosmic web could only have formed if most of the universe's matter was invisible, revealing itself only through its gravitational effects on visible matter. This dark matter wasn't just a minor correction to our understanding. It was a fundamental component of the cosmos that outweighed everything we could see by a factor of 5 to 1. The galaxies we had spent decades studying were merely the visible tips of massive dark matter icebergs, floating in an ocean of invisible material that dominated the universe's mass budget. The implications were staggering. If most of the universe was invisible, what did that say about our ability to understand the cosmos? How could we claim to comprehend the nature of reality when we couldn't even detect the majority of the matter around us? It was a humbling reminder that despite all our technological advances, we were still cosmic novices, struggling to understand forces and phenomena that operated on scales beyond our everyday experience. Yet rather than being discouraged by these discoveries, astronomers embraced them as new frontiers to explore. The existence of dark matter opened up entirely new areas of research, from particle physics experiments designed to detect these elusive particles, to computer simulations that modeled how dark matter might have shaped the evolution of the universe. The search for dark matter became one of the most important quests in modern science, involving physicists, astronomers, and engineers working together to solve one of the deepest mysteries of existence. Underground laboratories were built to shield sensitive detectors from cosmic radiation, while particle accelerators attempted to create dark matter particles in high-energy collisions. Meanwhile, space-based telescopes began to reveal galaxies in wavelengths of light that couldn't be seen from Earth's surface. Infrared observations showed star formation happening in dusty regions that had been hidden from optical telescopes. X-ray telescopes revealed the hot gas that filled the spaces between galaxies in clusters, heated to temperatures of millions of degrees by the gravitational energy of these massive systems. Each new wavelength of observation was like gaining a new sense, revealing aspects of galactic behavior that had been completely invisible before. Galaxies that appeared quiet and peaceful in visible light were revealed to be sites of violent activity when observed in radio waves or X-rays. Some harbored supermassive black holes that were actively consuming matter and blasting jets of high-energy particles across millions of light years. The universe was far more dynamic and energetic than anyone had imagined. Galaxies weren't just passive collections of stars drifting through space. They were complex, evolving systems engaged in constant interactions with their environment and with each other. They grew by consuming smaller neighbors, triggered bursts of star formation through gravitational encounters, and were shaped by processes operating on both the smallest and largest scales in the universe. This dynamic view of galaxies also revealed something profound about the nature of time in the universe. Because light takes time to travel across cosmic distances, looking at distant galaxies meant looking back in time. The farther away a galaxy was, the younger it appeared, showing us what galaxies looked like when the universe was in its infancy. These observations revealed that the early universe was a very different place from the cosmos we see today. Young galaxies were more chaotic, more active, and more prone to violent interactions. They were forming stars at rates that would be impossible in the present-day universe, creating brilliant regions of hot, young stars that blazed across cosmic distances. As astronomers pushed their observations to ever greater distances, they began to see galaxies as they existed when the universe was only a few 100 million years old. These ancient systems were smaller, more irregular, and more actively star-forming than their modern counterparts. They were the building blocks from which today's massive galaxies had been assembled through billions of years of cosmic evolution. The story of galactic evolution became inseparable from the story of the universe itself. Each galaxy was like a time capsule, preserving information about the conditions that existed when it formed and the processes that had shaped it over cosmic history. By studying galaxies at different distances and ages, astronomers could piece together a coherent picture of how the universe had evolved from its initial state to its current configuration. This historical perspective transformed our understanding of our own place in the cosmos. The Milky Way wasn't just our current home. It was the product of billions of years of cosmic evolution, assembled from smaller galaxies that had merged and grown over time. The very atoms in our bodies had been forged in the hearts of stars that had lived and died in previous generations of galaxies, their material eventually finding its way into the spiral system we call home. The realization that we were not just inhabitants of a galaxy, but products of galactic evolution, created a profound sense of cosmic connection. We weren't separate from the universe. We were part of it. made from the same materials and shaped by the same forces that had created the vast structures we observed in the night sky. This connection became even more meaningful as astronomers began to understand the role that galaxies play in creating the conditions necessary for life. The heavy elements essential for rocky planets and biological processes were forged in the hearts of massive stars and distributed throughout galaxies by supernova explosions. The spiral arms of galaxies like our own created regions of enhanced star formation, where new solar systems could emerge from the enriched material of previous stellar generations. Without galaxies, there would be no stars, no planets, and no life. These vast cosmic structures weren't just beautiful objects to admire through telescopes. They were the fundamental organizing principles of the universe, the frameworks within which all the complexity and beauty of the cosmos could emerge. The journey from viewing spiral nebulae as local gas clouds to understanding them as vast galactic cities represents one of the most profound shifts in human perspective in the history of science. It revealed not just the true scale of the universe, but our intimate connection to cosmic processes that operate on scales both vast and intimate. Yet, even as we've gained this cosmic perspective, new mysteries have emerged that remind us how much we still don't understand. The discovery of dark matter revealed that most of the universe is invisible, composed of mysterious particles that we can barely detect. The realization that cosmic expansion is accelerating pointed to the existence of dark energy, an even more enigmatic force that seems to be pushing the universe apart at an ever-increasing rate. These discoveries have forced astronomers to confront the humbling reality that the universe we can see and study directly represents only a tiny fraction of what actually exists. The galaxies that had seemed so substantial and permanent are now understood to be merely the visible peaks of massive dark matter mountains, floating in an ocean of invisible energy that dominates the cosmos. But perhaps the most remarkable aspect of this ongoing story is how it continues to unfold. Each new generation of telescopes and detectors reveals aspects of galactic behavior that previous instruments couldn't detect. The Hubble Space Telescope, named after the astronomer who first revealed the true nature of galaxies, has shown us galactic structures in unprecedented detail, while ground-based observatories equipped with adaptive optics can now peer through Earth's turbulent atmosphere to achieve resolution that rivals space-based instruments. Future telescopes promise to push these boundaries even further. The James Webb Space Telescope can observe the most distant galaxies in the universe, showing us these systems as they existed when the universe was barely a few 100 million years old. Extremely large telescopes being built on mountaintops around the world will gather unprecedented amounts of light, allowing astronomers to study individual stars and galaxies far beyond our local group. Each new observational capability brings the promise of discoveries that will challenge our current understanding and reveal new aspects of galactic behavior. The story of how we misunderstood galaxies for so long is far from over. It's simply the first chapter in an ongoing adventure of cosmic discovery that continues to unfold with each passing year. The transformation of our cosmic worldview from the early 1900s to today represents more than just a scientific revolution. It represents a fundamental expansion of human consciousness. We've learned to think on scales of space and time that challenge our ability to comprehend them, to see ourselves as part of a vast, evolving cosmos, rather than observers standing outside it. This expanded perspective has profound implications for how we understand our place in the universe and our responsibilities as conscious beings, capable of contemplating the cosmos. We are not just products of galactic evolution. We are the universe becoming aware of itself, capable of studying its own history and structure through the tools of science and observation. The galaxies that once confused our ancestors continue to hold secrets that we're only beginning to unravel. Each new observation adds another layer to our understanding, revealing the universe to be even more complex, more beautiful, and more interconnected than we ever imagined. And as we continue to push the boundaries of our cosmic knowledge, we're reminded that the greatest discoveries often come not from finding something new, but from realizing that something we've been staring at for years is completely different from what we thought it was. As we near the end of our cosmic journey through the greatest misunderstanding in astronomical history, it's worth reflecting on what this transformation in human perspective actually means for us today. The story of how we misunderstood galaxies for so long isn't just ancient history. It's a living reminder of how our most fundamental assumptions about reality can be completely overturned by new evidence and better tools. Consider the sheer audacity of what Hubble and his contemporaries were proposing. They were asking the scientific community to abandon everything they thought they knew about the scale of the universe and accept that what they'd been studying as local cosmic weather patterns were actually entire stellar cities containing billions of suns. It would be like discovering that what you thought were puddles in your backyard were actually vast oceans stretching to distant horizons. The psychological impact of this revelation extended far beyond the halls of academia. When the general public began to grasp the implications of these discoveries, it fundamentally altered humanity's relationship with the cosmos. Suddenly, Earth wasn't just a planet orbiting a star. It was a tiny speck in one galaxy among billions, scattered throughout an incomprehensibly vast universe. This shift in perspective coincided with rapid advances in photography and mass media, which meant that images of these distant galaxies could be shared with people around the world for the first time. The public became fascinated with these cosmic islands, these stellar cities floating in the darkness. Science fiction writers seized upon these ideas, creating stories about intergalactic travel and alien civilizations that might exist in these distant realms. But the transformation wasn't just about scale, it was about time itself. As astronomers began to understand that looking at distant galaxies meant looking into the past, they realized they were witnesses to cosmic history unfolding across billions of years. The universe wasn't just vast in space, but vast in time, with a rich evolutionary history that could be studied and understood. This temporal dimension added layers of complexity to galactic research that are still being explored today. When we observe a galaxy that's 10 billion light-years away, we're seeing it as it existed when the universe was only about 3 billion years old. We're watching cosmic adolescence, a time when galaxies were more chaotic, more actively forming stars, and more prone to dramatic interactions with their neighbors. The ability to observe galactic evolution in action has revealed that the universe is far more dynamic than early astronomers ever imagined. Galaxies aren't fixed structures carved in stone, but living systems that grow, evolve, and transform over cosmic time. They merge with neighbors, consume smaller companions, and sometimes undergo dramatic makeovers that completely alter their appearance. This dynamic view has also revealed the crucial role that environment plays in galactic evolution. A galaxy's fate depends not just on its initial properties, but on where it lives in the cosmic web. Galaxies in dense clusters experience very different evolutionary pressures than those in more isolated regions of space. Some are stripped of their star-forming material by interactions with hot intergalactic gas, while others continue to create new stars for billions of years. The environmental effects on galactic evolution have taught us that the universe operates as an interconnected system, with each component influencing every other component across vast distances. The cosmic web isn't just a convenient way to organize our observations, it's a fundamental aspect of how the universe works, channeling matter and energy across hundreds of millions of light-years. As our observational capabilities have continued to advance, we've discovered that galaxies are even more complex and varied than we initially realized. Some are dominated by massive central black holes that regulate star formation across the entire system. Others show evidence of having been completely disrupted by close encounters with neighbors, their stars scattered across vast regions of space. The diversity of galactic phenomena has forced astronomers to develop new theoretical frameworks for understanding how these systems work. Computer simulations now model galactic evolution over billions of years, incorporating the effects of dark matter, stellar feedback, and environmental influences. These models have revealed that the beautiful spiral structures we observe are often temporary phenomena, density waves that sweep around galactic disks like ripples on a pond. The realization that spiral arms are transient features was particularly striking because it challenged our intuitive understanding of these structures. What appeared to be permanent architectural features were actually temporary patterns created by the gravitational interactions of billions of stars. It was like discovering that the seemingly solid buildings in a city were actually made of flowing water, constantly changing shape while maintaining their overall appearance. This fluid view of galactic structure has profound implications for our understanding of cosmic evolution. If the features we observe are temporary, then galaxies must be constantly reshaping themselves in response to internal and external forces. The universe isn't just expanding, it's evolving, with each galaxy following its own unique evolutionary path through the cosmic web. The study of galactic evolution has also revealed the intimate connection between these vast structures and the possibility of life itself. The heavy elements essential for rocky planets and biological processes are forged in the hearts of massive stars and distributed throughout galaxies by supernova explosions. Without this ongoing process of stellar nucleosynthesis and element mixing, the universe would remain composed only of hydrogen and helium, incapable of supporting the complex chemistry necessary for life. The spiral arms of galaxies like our own play a crucial role in this process, creating regions where gas and dust can collapse to form new stars. These stellar nurseries are where the next generation of planets will be born, enriched with the heavy elements created by previous stellar generations. In a very real sense, galaxies are the factories where the ingredients for life are manufactured and distributed throughout the cosmos. This connection between galactic evolution and the possibility of life adds a deeply personal dimension to astronomical research. We're not just studying distant objects for their own sake, we're investigating the very processes that made our existence possible. The carbon in our bodies, the oxygen we breathe, the iron in our blood. All of these elements were forged in stellar cores and distributed by galactic processes operating over billions of years. The story of our galactic misunderstanding thus becomes a story about our own cosmic origins. The transformation from viewing spiral nebulae as local gas clouds to understanding them as vast stellar cities represents more than just a scientific revolution. It represents humanity's growing awareness of our place in the cosmic order. This awareness has continued to evolve as new discoveries have revealed even more surprising aspects of galactic behavior. The detection of gravitational waves from merging black holes has opened up entirely new ways of studying these cosmic events. The discovery of exoplanets orbiting stars in other galaxies has raised tantalizing questions about the possibility of life beyond our own galactic neighborhood. Each new revelation adds another layer to our understanding of how galaxies work and how they've shaped the universe we inhabit. The simple spiral nebulae that once puzzled our ancestors have become windows into the deepest mysteries of existence itself. They've taught us about the nature of space and time, the role of dark matter and dark energy, and the processes that govern cosmic evolution on the largest scales. Yet even as our knowledge has expanded dramatically, we're constantly reminded of how much we still don't understand. The discovery that most of the universe is invisible, composed of dark matter and dark energy that we can barely detect, has humbled our cosmic pretensions. The realization that galaxies are embedded in a vast cosmic web of structure has revealed the universe to be far more complex and interconnected than we ever imagined. This ongoing process of discovery and surprise is perhaps the most important lesson from the story of our galactic misunderstanding. Science isn't about achieving perfect knowledge. It's about constantly refining our understanding through careful observation and measurement. Each new discovery not only answers old questions, but raises new ones that challenge our assumptions and push the boundaries of human knowledge. The transformation of our cosmic worldview over the past century demonstrates the power of human curiosity and ingenuity. When faced with observations that didn't fit established theories, astronomers didn't give up or retreat into dogma. Instead, they developed new tools, refined their techniques, and remained open to the possibility that their fundamental assumptions might be wrong. This willingness to question established wisdom and embrace new evidence is what drives scientific progress. The astronomers who first suggested that spiral nebulae might be distant galaxies were challenging not just technical details, but the entire framework of cosmic understanding. They were asking their colleagues to imagine a universe so vast and complex that it defied human comprehension. The fact that this transformation succeeded, that the scientific community ultimately embraced the evidence for an expanding universe filled with billions of galaxies, demonstrates the self-correcting nature of scientific inquiry. Truth has a way of emerging through the accumulation of evidence, even when that truth challenges our most cherished beliefs about the nature of reality. As we look toward the future, we can expect this process of discovery and revision to continue. New telescopes and detection methods will undoubtedly reveal aspects of galactic behavior that we can't currently imagine. The story of how we misunderstood galaxies for so long is far from over. It's simply the first chapter in an ongoing adventure of cosmic exploration that will continue as long as humans look up at the night sky and wonder about their place in the universe. The galaxies that once confused our ancestors continue to hold secrets that challenge our understanding and inspire our imagination. Each new observation adds another piece to the cosmic puzzle, revealing the universe to be even more beautiful, more complex, and more mysterious than we ever dared to imagine. And in that ongoing mystery lies the true wonder of scientific discovery, the recognition that no matter how much we learn, there will always be new horizons to explore and new questions to answer. In the end, the story of our galactic misunderstanding teaches us something profound about the nature of knowledge itself. Our understanding of the universe is always provisional, always subject to revision in light of new evidence. What seems certain today may be overturned tomorrow by observations that push the boundaries of what we can detect and measure. But rather than being discouraged by this uncertainty, we should embrace it as the engine of discovery. The fact that the universe continues to surprise us means that there are always new wonders waiting to be uncovered, new mysteries to be solved, and new perspectives to be gained. The journey of understanding is never complete, and that's what makes it so endlessly fascinating. The transformation from cosmic claustrophobia to cosmic perspective represents one of humanity's greatest intellectual achievements. We've learned to see ourselves not as the center of creation, but as participants in a vast, evolving cosmos that connects us to every star, every galaxy, and every corner of the observable universe. It's a perspective that's both humbling and inspiring, reminding us that we're part of something much larger than ourselves, while celebrating our unique ability to contemplate and study the cosmos that gave us birth. The implications of this cosmic revelation extended far beyond the realm of professional astronomy, seeping into the very fabric of human consciousness, and fundamentally altering how we understood our place in the grand tapestry of existence. When Edwin Hubble's discoveries finally gained widespread acceptance in the 1930s, they didn't just change textbooks, they transformed the human soul's relationship with infinity itself. The profound psychological adjustment that ordinary people had to make when confronted with this new cosmic reality. For generations, humans had lived with the comforting notion that the universe was a manageable, comprehensible place. The stars were distant suns, certainly, but they were all part of our cosmic neighborhood. The fuzzy patches of light that telescopes revealed were simply nearby clouds of gas and dust, decorative elements in our familiar galactic home. Suddenly, humanity was forced to confront the reality that each of those innocuous spiral nebulae contained more stars than there are grains of sand on all the beaches of Earth. The universe hadn't just gotten bigger, it had become inconceivably, almost incomprehensibly vast. Every direction you looked in the night sky revealed not just distant stars, but entire cities of stars, each containing billions of suns, many potentially harboring worlds of their own. The cultural impact was immediate and profound. Religious leaders grappled with theological implications they had never needed to consider. If the universe contained billions of other galaxies, each potentially hosting countless worlds, what did that mean for humanity's special place in creation? Philosophers debated whether human existence could have any meaning in such an enormous cosmos. Writers and poets found themselves struggling to capture the sublime terror and wonder of this new cosmic perspective. Science fiction, still in its infancy, exploded with new possibilities. Authors like H.G. Wells and Jules Verne had imagined travels to the moon and planets, but now writers began to dream of journeys between the stars and even between galaxies. The concept of alien civilizations took on new dimensions when there were billions of potential homes for extraterrestrial life scattered throughout the cosmos. But perhaps the most profound impact was on our understanding of time itself. If these galaxies were millions of light years away, then the light we were seeing from them had been traveling toward us for millions of years. We weren't just looking at distant places. We were looking into the deep past, witnessing the universe as it existed when our planet was young and life was just beginning to emerge from the primordial oceans. This temporal dimension added an almost mystical quality to astronomical observation. Every photon of light captured by a telescope was a messenger from the ancient past, carrying information about cosmic events that had occurred when the universe was fundamentally different from what we see today. Astronomers weren't just studying space, they were becoming time travelers, archaeologists of the cosmos, piecing together the history of creation itself. The realization that we could observe cosmic evolution in action by looking at galaxies at different distances was perhaps the most revolutionary concept of all. By comparing nearby galaxies to those at increasingly remote distances, astronomers could literally watch the universe change and evolve over billions of years. It was like having a time-lapse movie of cosmic history, revealing how the structures we see today had emerged from the chaos of the early universe. This historical perspective revealed that the cosmos was not the static, eternal realm that philosophers had imagined for millennia. Instead, it was dynamic, evolving, constantly changing on scales so vast that human lifetimes were mere flickers in the cosmic story. Galaxies formed, evolved, merged, and transformed in an ongoing dance of creation and destruction that had been playing out for billions of years before Earth even existed. The discovery that the universe had a history also raised profound questions about its future. If galaxies were moving away from each other, as Hubble's observations suggested, then the cosmos was expanding, and if it was expanding now, logic dictated that it must have been smaller in the past. Following this reasoning to its ultimate conclusion led to one of the most startling insights in the history of science. The universe itself had a beginning. This concept of cosmic birth, later dubbed the Big Bang, was so revolutionary that many astronomers initially rejected it outright. The idea that all of space, time, matter, and energy had emerged from a single point in the distant past seemed more like mythology than science. Yet as more evidence accumulated, this radical notion became increasingly difficult to dismiss. The implications were staggering. If the universe had a beginning, then everything we could observe, Every galaxy, every star, every planet, every atom had emerged from that primordial moment of creation. The cosmic history written in the light of distant galaxies was not just the story of how these structures had formed, but the story of how everything in existence had come to be. This realization transformed our understanding of matter itself. The heavy elements that make up planets and living beings hadn't existed in the early universe. They had been forged in the nuclear furnaces of stars, created through processes that took billions of years to complete. The carbon in our bodies, the oxygen we breathe, the iron in our blood. All of these elements had been manufactured in stellar cores and distributed throughout the cosmos by the violent explosions of dying stars. We were not just inhabitants of the universe, we were products of cosmic evolution, made from stellar debris that had been cycling through space for billions of years. The atoms that compose our bodies had been part of countless other structures throughout cosmic history, perhaps existing in the atmospheres of distant worlds or the cores of ancient stars, before eventually finding their way to Earth and becoming part of living beings capable of contemplating their own cosmic origins. This connection between galactic evolution and the possibility of life added a deeply personal dimension to astronomical research. The spiral arms of galaxies like our own weren't just beautiful patterns to admire. They were the cosmic factories where new stars were born, where planets formed, and where the conditions necessary for life were created and maintained. Without the ongoing processes of stellar birth and death that occur in galactic environments, the universe would remain a sterile realm of hydrogen and helium, incapable of supporting the complex chemistry that makes life possible. The story of our galactic misunderstanding thus became inseparable from the story of our own existence. The transformation from viewing spiral nebulae as local phenomena to understanding them as vast stellar cities wasn't just an abstract change in scientific theory. It was a revelation about the very processes that had made our existence possible. We were not separate from the cosmic dance of galaxies. We were part of it, temporary arrangements of matter that had achieved consciousness and were capable of studying the universe that created us. This profound sense of cosmic connection continues to deepen as our understanding of galactic evolution advances. Modern astronomy has revealed that galaxies are not isolated systems, but part of a vast cosmic web that connects all structures in the universe. The dark matter filaments that stretch across hundreds of millions of light years are like cosmic highways, channeling matter and energy between distant regions of space and influencing the evolution of galaxies across the entire observable universe. The recognition that we live in an interconnected cosmos has fundamental implications for how we understand our place in the universe. Every galaxy, no matter how distant, is connected to every other galaxy through the invisible threads of gravitational influence. The expansion of space itself is carrying these structures apart, but they remain linked by the common history they share and the ongoing processes that continue to shape their evolution. As we stand at the threshold of a new era in astronomical discovery, with telescopes capable of peering deeper into space and further back in time than ever before, we can be certain that more surprises await us. The story of how we misunderstood galaxies for so long is not a closed chapter in the history of science. It's a continuing narrative that reminds us of both the power of human curiosity and the endless capacity of the universe to astonish us. The transformation of our cosmic perspective over the past century represents one of the greatest intellectual achievements in human history. We've learned to see ourselves not as isolated observers standing outside the universe, but as participants in a cosmic story that began nearly 14 billion years ago and continues to unfold around us every day. The galaxies that once confused our ancestors have become our guides to understanding the deepest mysteries of existence, teaching us about the nature of space and time, the origins of matter and energy, and our own place in the grand scheme of creation. In the end, the story of our galactic misunderstanding teaches us something profound about the nature of knowledge itself. Our understanding of the universe is always evolving, always subject to revision in light of new evidence and better observations. What seems certain today may be overturned tomorrow by discoveries that push the boundaries of what we can detect and comprehend. But rather than being discouraged by this uncertainty, we should embrace it as the engine of discovery, knowing that the universe will continue to surprise us, challenge us, and inspire us for generations to come. The journey from cosmic claustrophobia to cosmic perspective represents humanity's greatest expansion of consciousness, revealing us to be not the center of creation, but something far more remarkable. The universe becoming aware of itself, capable of studying its own history and contemplating its own future. And in that ongoing contemplation lies the true wonder of our existence, the recognition that we are both infinitesimally small and cosmically significant, temporary arrangements of stardust that have achieved the extraordinary ability to understand the very forces that brought us into being. I hope you had an amazing night with me. I'll see you again tomorrow. Until then, stay curious, keep wondering. This is Boring Science signing off. Good night. Cheers.